Hi, this is Forrest Judd from Hagerman & Company, and today I'm going to show you how to perform a frequency response analysis in Autodesk Simulation Mechanical 2016. For this demonstration, we're going to use a simple model. We have a steel base plate, we have a few isolator pads, and then we have a plate on top of those pads. To begin the analysis, we launch the model into Simulation Mechanical 2016. That's going to perform the necessary model translation so we can perform the analysis. Then once we have the model in Simulation Mechanical, we're going to start by generating a mesh. Now we can generate the mesh using either some qualitative settings like a coarse or fine mesh, or we can apply more specific settings like an absolute mesh size. We'll just stay with the qualitative for now. This is going to not only mesh our model but specify our element type. So we're using bricks in this case. We can review the mesh, and I think for this analysis this is going to be sufficient. Now note we're going to perform a natural frequency analysis to begin with. This is a prerequisite for the frequency response analysis. The frequency response analysis in Simulation Mechanical is a modal superposition, so we must have those normal modes in order to perform the frequency response analysis. Notice that our analysis type is also a linear natural frequency analysis. While we can perform nonlinear natural frequency analyses with Simulation Mechanical, the frequency response analysis is a linear analysis. So to feed that analysis we must have linear modal results. Nonlinear modal results will not work. You must have the linear modal results. Next we'll apply materials. So for our base plate and the table, those are straightforward. We're just going to make those out of steel. The rubber material may be a bit more difficult. Rubber is inherently nonlinear, but in this case we need to somehow approximate this material in a linear fashion. We're going to have to derive linear material properties for this rubber. Now it can be difficult to determine the material properties that you need to use, especially for elastomers, but for assuming small deformation, in this case is our ultimate goal, then it's generally safe to assume a constant modulus for the rubber. So I'm going to modify the material properties here, and in this case we're going to use a density of 1.2 grams per cubic centimeter. And just so I don't have to do too much math, I'm going to switch my units so that I can provide my modulus in megapascals. So again, we're going to modify our rubber material. And say for nitrile 50 Shore A, I've seen reference to modulus of elasticity of approximately 1.5 megapascals. And for our Poisson's ratio, we'll leave that at 0.47. Again, your material properties could differ significantly. Okay, so we have some materials defined. We have our mesh defined. In our application, we're assuming our table is fixed. So to eliminate our rigid body motion, we are going to provide a general constraint on the base of this that's going to be fixed. And then the remainder of our model, we're going to have contacts that are bonded. So our default contact type is bonded. So in Simulation Mechanical, we don't need to specifically assign contact types to those faces unless they're different from the default. For the remainder of the setup, we ultimately need to describe how many modes do we want to calculate. If we say that rigid body modes are expected, we can have the system sort of ignore those rigid body modes. We're not expecting those since we have contact specified, and we have our boundary condition that our plate is fixed. So we'll go with 5 frequencies to calculate. Now we could also choose, rather than defining an explicit number of frequencies to calculate, we can instead choose a range. So if we know that our application is going to be excited through a certain range of frequencies, or within a certain range, if we're only interested in that, then we can specify that range of both a lower and an upper cutoff frequency. So for example, we could say our application is not going to experience anything below 5 Hertz or really anything above 200 Hertz. You might say 5 to 200. This is also a good way to eliminate, if you don't have any constraints on your system when you run the analysis, your first 6 modes are going to be at or near 0. You could put a non-zero value for the lower cutoff frequency that would then ignore the first 6 rigid body modes. But in this case, we're going to be more general. We're going to calculate 5 modes. And with that, I believe we're ready to solve. And thanks to the magic of video editing, the solution happened just like that. So it's important to note when you're reviewing the results of a modal analysis that any displacements you see should not be treated as absolute values. We've not actually excited this model with any sort of cyclic load. These are all relative displacements. So the way the parts move relative to each other are an indication of the range of motion you might experience when the system is excited at a particular frequency. The absolute values, these are definitely not displacements that you would see if the system was excited at this frequency. To get specific displacements, we need to perform a different type of analysis, which we'll do shortly. But it's important to review each of these modes to get an idea of what the frequencies are. So in the lower left here, you see this is mode 1 at a frequency of about 18 Hertz. And we can investigate the motion. In this case, if we were to excite the system at this frequency, we would expect to see oscillating motion back and forth like this. And I think that makes sense intuitively if you have any experience with this kind of sort of device. We can investigate the remainder of the modes. Remember, we calculated 5 by advancing through our load cases. So we have a second natural frequency at about 18 Hertz, then at 24, 40, 50. And at each of these modes, you can get an idea by animating what the motion is. So what we're really seeing here is each of these modes is sort of a different way that these rubber pads could deflect depending on the way the system is excited. So it's a range of motion in a particular direction. Okay, so now armed with these results, our natural frequencies or our normal modes, we can use this as input into a frequency response analysis. So rather than just in general saying, well, what are the frequencies at which this system is likely to resonate, we can investigate either at specific frequencies or around our normal modes what will be the actual displacement of the system when excited in certain ways. So that's where the frequency response analysis comes in. So the best way to perform this is to simply copy the design scenario into a new one. So we can say here that we want now a frequency response analysis, and by changing the analysis type of the existing design scenario, we can tell the software we would like to first copy the design scenario and then change it. So what this is going to do is it's going to keep the same setup for everything, the same material definitions, the same boundary conditions, and so we've got a really good start on our analysis to begin with. So all we really need to do is then provide the new information specific to this analysis type. So with our frequency response analyses, you notice our setup tab is quite bleak. There's only one button here. It's because all description of loading of the system happens in the setup parameters dialog. So this dialog is somewhat complex, but when you really dig into it, it's relatively straightforward. The most important part of this dialog is we need to tell this analysis which design scenario in this same file has the modal results. Again, our frequency response analysis in Simulation Mechanical is modal superposition, so we must have those normal modes already calculated, and we point to those calculated modes by indicating which design scenario in this same file has those results. We can have lots of different design scenarios. One of them has to be the normal modes. So the material definitions have to match and everything. So that's why it's best to just copy the scenario and change the analysis type rather than create a whole new scenario from scratch. Now we have various settings in this dialog. The most important part of this, I would say, aside from the modal results specification, is how are we exciting this system? Where is the excitation happening? At what frequencies is it happening? And what is the amplitude of that excitation? Now, by default, any of our fixed nodes, we can say that the excitation is happening at those nodes, which in a lot of cases is what you want. Like in this case, we have an isolator here. We've got some equipment here that we need to minimize vibration on. And so ideally it's our system as a whole that is being excited, and we want to investigate the effect of having these rubber pads, this size, this spacing. How is that going to damp the system? So in this case it's perfectly fine to indicate that our excitation should happen at every base node, every node that is defined as fixed. Now, in a situation where the excitation is happening elsewhere, or if we want to investigate, specific locations at the model of where that excitation is happening, we ultimately need to create a set of nodes based on number that the excitation will take place at. But in most cases, we're going to stick with the base. Now, we need to describe the type of load. Specifically, what direction is the excitation happening in, and then at what frequency. Now notice this is a frequency index. This comes from the next tab. So this tab here indicates what frequencies we're interested in investigating. Now generally we're going to want to check this box to include the natural frequencies. So this is going to take the modal results, and at each of those frequencies we're going to investigate the excitation if our load, if our excitation happens at those natural frequencies. If we're also exciting the system at other specific frequencies, we can add those frequencies to the list. Now this area is where if we had a different frequency index, so if we had a different excitation at different frequencies, we would add a new frequency index if the loading type was different. So if we're loading in the Y direction with a different set of frequencies, we might need to create a different frequency index. In this case, we're just going to add right to this list, say at 30 Hertz. Maybe we know we've got some device sitting on the table that is vibrating at that frequency. Our damping ratios, if we want to include damping, we can do that here. The next tab is our amplitude. So basically at a given frequency, what acceleration are we experiencing in G's, or what force is being applied, in this case, based on our unit type, in newtons. So this is actually going to provide a curve. So we don't necessarily have to, unless we know at, say, each natural frequency, if there's a corresponding acceleration at that particular frequency, we could provide that here. Otherwise, the excitation at a given frequency will be interpolated from this curve. So if if we're exciting at say at 0 hertz, if we were seeing, maybe we want to investigate 4Gs. So what we might do is just add 2 rows to this table, encompassing the entirety of our expected frequency, like the domain. And if for whatever reason we've provided frequency that goes outside this domain, ultimately it'll take whatever was closest. So if this happened to be 2 to 4, if we had 120 hertz we were exciting at, it would stick with the 4G acceleration. It's only going to interpolate during this part of the curve. Alright, so we've described the acceleration that we would be expecting across a range of frequencies that will encapsulate our entire study. We're indicating that we want to include our natural frequencies and also investigate excitation at 30 hertz. And we're providing that acceleration, in this case we've set in the x direction, so sort of back and forth. So let's just go with that and see what we get. Oh, one last thing, we do need to specify some damping. Damping is going to be present everywhere. This damping ratio is defined as a fraction of critical damping. So again, we'll do a curve here over the same range, 0 to 100 hertz, and we'll just go with, so in this case we'll just go with, say, 5%. And with that we can review our results. So in this case we have 6 load cases, because if you recall, we specified that we wanted to investigate excitation at each of the natural frequencies or normal modes from our original study, which was 5, and then also at 30 hertz. So you can see in our load cases down here we have 6 load cases, and it does describe the excitation frequency. So you can see at each of these cases, remember, at about 18 hertz, about 25 hertz, the 30 hertz that we specified, and then the last 2 natural frequency we had calculated. So this is going to give us an idea. Now this displacement is more of a real-world displacement. Now again, keep in mind we performed a linear analysis, and we're using a fundamentally nonlinear material. So if our displacements are large, we may want to really carefully think about the results that we're getting. Like in this case, 3 millimeters, 2 millimeters. This is an exaggerated displacement that we're seeing. If we want to get a look at the actual displacement, this is what we're seeing in terms of actual displacement. So 25 hertz looks to be a pretty bad situation for us here, and that does look to be the worst. 25 hertz at 4 Gs would probably cause us some trouble if we're trying to keep this still. So in our results type we can look at both in phase, out of phase, and square root of the sum of the squares, and then our other results. So that's it for this demonstration. I hope you found it informative, and thanks for watching.